Hello, good afternoon, everyone. Thank you for joining our seminar today. And we are at the regular geotechnical seminar series. Before we start, I would like to remind everyone to please put your devices on silent mode and be ready to participate in the Q&A at the end. We will also circulate an attendance sheet in the room. And today we have a seminar or the conference about the IT Highway Design and Construction Considerations by Ed Grozic. And talking about Ed Grozic, he's a principal consultant and director of strategic projects with Tetra Technology or with the Tetra Tech Canada Inc. He also bachelor degree in civil engineering and MS in geotechnical engineering from the University of Alberta. Ed Grozic has 28 years of work experience on northern transportation, infrastructure, energy mining, and environmental cleanup projects for public, private, and indigenous clients. His permafrost and geotechnical skills include engineering design, field reconnaissance, and routing evaluations, geophysical investigations, granular and rock resource assessments, and construction projects across the Arctic, specific to linear infrastructure, fiber optic communication, and energy projects. He is contributing author to the Transportation Association of Canada, Guidelines for Development and Management of Transportation Infrastructure in Permafrost Regions, Canada, and Canadian Standards Association Plus 4011.1, Technical Guide, Design and Construction Consideration for Foundation in Permafrost Regions, and the Bureau of Normalization du Quebec, BNQ, Standard Development on Risk-Based Approach for Community Planning in Northern Regions. He is also the general manager of two indigenous-owned joint venture consulting engineering companies. They are Netrub EVA Consulting Limited in the Wedge in settlement area and Tuktoyaktuk EVA Consulting Limited in the Inuvik settlement region, Northwest Territories. Now, Ed Grozic, the floor is all yours. You can start your conference. Thank you.
All right. Thank you, Daniel, for the introduction and for the opportunity to speak today on the Inuvik Tuktoyaktuk Highway. And you said that pretty good. It's the Inuvik settlement region, and the ITH is within the ISR. So I'm glad to be here today. I'm going to be switching between the camera and my other monitor here. Today, I'd like to speak specifically to this construction of this road, this piece of linear infrastructure, and over the 10 years that this project was ongoing on a pretty accelerated timeline, but it's hard to believe that 10 years can be an accelerated timeline. The image that you see up on the screen, you'll see two pingos in the background. The Inuvik Tuktoyaktuk Highway, a gravel road, is in the foreground, and this is maybe about 5-6 kilometers south of Tuktoyaktuk. And just as an FYI, the pingo closer to your image or to you is the Inuvik pingo, and it's one of the highest in the world. It's about 49 meters tall and about 300 meters wide. Today, I'll speak about the Inuvik Tuktoyaktuk Highway, about its background, and then dive into the routing, terrain mapping, geotech investigations that we undertook, the embankment design approach that was undertaken, the borrow materials that we had available to us. This is all winter construction, which I'll speak to as well. And then 8 bridges, and the ground temperature monitoring that's happening as currently. It's ongoing, and it's a bunch of monitoring that's ongoing. So the ITH, and most probably know this by now, but it is the only road in Canada to the Arctic Ocean, and actually it's the only road to the Arctic Ocean, but it's only connected by one road that crosses the Arctic Circle, and that's the Dempster Highway. And in North America, there's actually only 2 roads that cross the Arctic Circle, and the other one to the Dempster is the Dalton Highway in Alaska. So that's only 2 ways to cross the Arctic Circle and get to the Arctic Ocean, either the Canadian or the American Beaufort side. In 2008, the hamlet of Tuk, Inuvik, and the GNWT secured funding from the federal government, and at the time it was Prime Minister Harper, and secured funding in the order of $150 million for engineering and environmental investigations, preliminary design, all in support of construction of a road between Inuvik and Tuktoyaktuk. That 150 was increased an additional $50 million by the federal government, and then the Department of Infrastructure, the Department of Transportation within the GNWT contributed another $100 million. So the project had $300 million to work with, and it was kind of like a design build in that the owner, the GNWT, negotiated with a contractor, a local contractor, which was E. Grubens Transport and Northwind Industries, and that negotiated contract, then the owner and the contractor selected a design team, and a design team ended up being 2 firms, of which Tetra Tech was one. Here's an aerial image of the ITH, its location geographically in Canada, in the top left, and then the route between Inuvik and Tuktoyaktuk. Like I mentioned, the owner was a GNWT, contractor was, the acronym is EGT Northwind, and a design team was Tetra Tech and Stantec through our indigenous partner companies, which is Kigiaki BA for Tetra Tech and Kavik Stantec for Stantec. So it was an entire team, dozens of people working on this project for many years. There's no one individual or small group. There was many. A negotiated contract, like I said, and the owner was pretty clear about what their expectations were, and that was to construct a resilient gravel road, a resilient, cost-effective gravel road, and to maximize local resources, workforce, and equipment. They were able to do that by engaging the local contractors, but our role was to design a resilient, cost-effective road. The materials needed to be local, borrowed materials, and materials available in this region between Inuvik and Tuk are pretty limited. And because this part of the world is in a continuous permafrost environment, and the tundra is too soft and wet to work on in the summer months, then this work was done between November and, let's say, November and April in the winter months, rather than a May to October type of construction season that we would have down south. This road alignment, it crosses 2 distinct physiographic regions between Inuvik and Tuk, and you don't clearly see it here. There was really good mapping that was done by Rampton and Ross Mackay back in the 70s and 80s, but the southern third of the alignment crosses what is termed the eastern extension of the Caribou Hills, and it's common till, morainal, and glacial fluvial deposits, and with varying quantities of ground ice, and overburden is less than 50 meters thick, just as a generalization. The northern 2/3 of the alignment, though, is is the coastal plain, or the Tuktoyaktuk lowlands, or coastlands that it's often called. And you can see in this image quite well that the area, the region is just littered with lakes. And then the soils are more lacustrine and glacial fluvial deposits, and ground ice and massive ice lenses are common, widespread throughout the area. Bedrock closer to the ocean is deeper, so it's more than 50 meters deep. So bedrock and the use of rock for our project wasn't an option because of its depth. In 2009, we undertook a field reconnaissance. I'll walk you through the stages of a project. We went from nothing, no direction, as a design team. We had to identify an alignment that could work for us, that we could construct with. And so in 2009, in the fall, we undertook a field reconnaissance program. We flew a line, broadly flew a region that the Public Works Canada in the 1970s identified as a possible route between Inuvik and Tuktoyaktuk. And from that, we worked with that routing and refined and refined and re-refined and reworked a route that basically crossed the most favorable terrain conditions that we had available to us and tried to avoid the most least favorable permafrost and organic terrain conditions, and to find a routing that we could do a LiDAR survey on a corridor that then we can actually put a geometric alignment to. There were a bunch of setback distances that we had to meet for environmental reasons, setbacks from Husky Lake, archaeological constraints, all sorts of, and of course, finding an alignment that was close to available borrow material was important as well. So stuff that we were looking for in the field that we were trying to stay away from, quite common in periglacial permafrost environments, is the ice wedge polygonal terrain that you can see in the top left. This part of the world has retrogressive thaw flow slides that you see in the right image. Lacustrine deposits are pretty widespread near Husky Lake, and of course close to the Beaufort Sea. And then we were also trying to route stay away from steep side slopes, and then we were trying to stay away from ice and excess ground ice in soils. But in this part of the world, there's a lot of excess ground ice in the soils, as we found through investigations, which I'll speak through. So what's excess ground ice? Or when I refer to excess ground ice, some people will refer to ice rich, but it's ground with excess ice. And what does that mean? Well, when that frozen mass of ice and soil, when it thaws, what happens? The solids separate from the water. And this image here is just illustrative of what happens in that case. So it's a very thaw sensitive material. Obviously, when that material becomes saturated or super saturated, in this case, there's a loss of shear strength, there's excessive settlements. And so the design team in this part of the world worked hard to try to keep this material frozen, which it's strong in a frozen state and it's very weak in a thawed state. A bunch of terrain map. Once we knew a general route and identified a corridor, then detailed terrain mapping was undertaken. And this took a lot of effort. And this detailed terrain mapping then was used to then target the most, what we considered the most favorable terrain units for this road alignment that we had to work with. And then we also used that to be able to put a geometric alignment on. So this is just an example of one of the profiles of the geometric alignment. We needed to design a road, highway standard road, to meet TAC standards, and we needed to design to a design speed. So in this case, what was selected was an 80 km/h horizontal geometric standard design speed, and then because of the vertical up and down, then the design speed for the ITH is 70 kilometers an hour. If we would have gone to a higher 80K design speed, then that would have required even more boron materials. And so then this alignment ended up being further refined because we knew what terrain types we liked and what terrain types we wanted to avoid. But when you put a road geometric alignment down onto that terrain mapping, it didn't always align with the most favorable terrain. And there are certain sections of the road that had to cross unfavorable terrain. We were aware of it, and then we had to design accordingly for it. Geotechnical investigations were undertaken, had to be in a winter, 2 winter seasons, and because this is a remote location, there was no communication or connection between Inuvik and Tuktoyaktuk on land. It was formerly via an ice road. Then it was done between February and March, and it was used just compacted snow roads were used, and nod wells and other track carriers. And pulling equipment or trailers on sleigh, like you see here, we're done. And we started in February and March because we started to get a little more daylight hours. Trying to do work in December and January is very difficult. And then there's a couple hours of, well, there's a couple months there of no real daylight, great daylight hours. And so it's more favorable to start a drilling program in February and March, and sometimes occasionally work into April. Part of the investigation was looking at boron material, which we knew we needed to construct a road. Almost 5 million cubic meters of material was required to construct the embankment, and so no geophysical surveys were done at the time. 10 years later, we'd probably undertake some geophysical surveys, but it was just a detailed conventional drilling program. And this is just an example of the concentration of the holes. And you can see the outline of these 2 deposits, which appeared favorable from the mapping, and then we needed to investigate them. And so this was done on probably 9 sources along the ITH. We also undertook geotechnical investigations at stream crossings and along the proposed alignment to better understand what the subsurface conditions were, what the ground temperature conditions are, and to better understand the stream crossings, whether we were dealing with talix or what sort of a subsurface condition exists. What we found consistently through well, let's say these 13 these stream crossings, is we found consistently a silty clay material, and it was ice rich. So the silty clay material was dominantly till from a depositional history environment. It was a till, but it was quite ice rich, and it was fine grained, and most of the crossings encountered that. From this geotechnical investigation that we collected at the crossings and along the road alignment, then we started to develop what I would call soil profiles in support of then being able to do thermal analysis. So I'm stepping through these different processes, but we had to understand what the subsurface conditions are. We know it's going to be variable along 140 kilometers of road, but we still needed to develop some typical profiles that then we can use in thermal analysis and in design, in stability analysis and the other design that still needed to happen. And so at the time we developed a profile A, B, and C, not uncommon, but these were consistent stratigraphies that we were encountering. Thick organic soil cover over lower ice content material, which was occasionally encountered, but more commonly a thick organic cover over high ice content material. Sometimes we just encountered simply thick peat, so like a peat plateau or some sort of a thick peat deposit, which we tried to avoid if we could from a geometric routing perspective. Through the investigations, we collected a bunch of ground temperature data. So many of the holes, ground temperature cables were installed. We knew the general, from previous work by others over the decades, the general ground temperatures in the regions, and we do work in Inuvik and Tuktoyaktuk, so we know the temperatures are there, but we didn't know how they varied along the route. And so these are just profiles of ground temperature variability between Inuvik and Tuk, and you can see from minus a little bit colder than -5 to 1 anomalous to -1, but -2 to -5 was the common range of subsurface ground temperature temperatures that we encountered at depth. And the ground, as you would expect, ground temperatures got colder from south to north. Also collected some ground temperature data along the alignments, separate from the stream crossings, which supported the same. From the ground temperature data and the subsurface geotechnical investigations, and knowing that we needed to construct a highway to a geometric design standard, then we started to put pieces together. Okay, what's the embankment cross section going to look like? This is a conventional embankment cross section that you see here. We were mindful of the fact that steepening side slopes would be more favorable in terms of reducing material quantities, shallowing the side slopes, a little more stable embankment, but larger footprint, greater material quantities. And so all that work of optimizing the right embankment for the right terrain conditions, all that work was still ahead of us. Part of the work was to understand then what minimum embankment heights did we need, or were we going to use along this alignment. And so from the geotechnical investigations, we generalized to 4 common terrain types along the route. Obviously, there's many terrain types, but 4 were generalized, the common ones that you can read here. And it was these 4 generalized terrain types that then we started to undertake ground thermal analysis on. Maybe I should, yeah, okay. And so part of the geotechnical design considerations were putting this embankment or wanting to construct the embankment was not just the subsurface soil conditions, but also what about the embankment fills, and the two are interconnected. So we did some parametric basically stability analysis looking at embankment fills, not just the height of fills, but height of fills on cross slopes, and how much of a cross slope could we put a road on that would still be stable, and what would be the maximum cross slope that we could place the embankment on. What is the maximum height that we could construct? We weren't interested in necessarily maximizing embankment height because that took more material volume, but geometrically sometimes the road required higher embankments just to get through depressions and deeper areas. Varied subgrade conditions. Of course, we looked at that and how then the embankment perform on these variable subgrade conditions. But if we're able to construct a thick enough embankment and maintain the permafrost at around the original grade, then we assumed that the frozen subgrade would be more rigid than the embankment materials itself. We looked at the height or the thickness of the deeper fills and how the deeper fills would perform on very ice-rich flat ground from a creep perspective. So these embankment fills would be spread over time. How long would it take? How high of a fill, an embankment fill, could you construct? And sometimes for geometric reasons, then roads were they may have been moved or realigned or from a side slope or the embankment height decreased from a stability perspective. There are a bunch of factors that one had to go through when finalizing a route or optimizing a route is a better term, from a geometric alignment perspective, from a terrain perspective, from material availability, because the embankments were constructed with different materials as well. And all of that one had to understand all of that and where the risks were from a non-performance on sections of the embankment. Stability analysis was pretty comprehensive, and it looked at many different scenarios. We were interested in understanding how high of a fill we could construct. We ended up through our analysis determining that a 5 meter thick fill with 2-to-1 side slopes from a stability perspective, generally it worked, unless the subsurface conditions were too soft and the strength wasn't there. With a frozen subgrade, a 5 meter embankment, 2-to-1 side slopes, 2.5-to-1 side slopes worked just fine. We did some parametric work to try to steepen up the side slopes to reduce fill quantities, and of course, if fill heights can be reduced, then the likelihood of failure decreases and the maintenance requirements decrease. Higher fills are just fundamentally more work to construct them, more work to maintain. I spoke about the borrow sources, and I'll mention them more now. There isn't a lot of material that's available between Inuvik and Tuk. I think there were 9 or 10 sources that were investigated from a desktop perspective that had the right attributes, and I think 9 were drilled during the geotechnical investigations. Only 7 of them were ultimately developed, and this is an image showing the 7 sources. The work was done in a winter, so everything had to be drill and blast, and then the frozen materials were hauled to the alignment. The material dominantly in this part of the world is a silty, fine to medium grain sand. There was one borrow pit here, 312, that had a nice sand and gravel. That would be the optimum material to use for the embankment as a whole, but the haul distances were just too great to go from 312 all the way up to the north end or all the way down south. So the road, from a construction cost perspective, was the embankment was constructed with generally the closest available material sources. And a couple of the sources were only actually accessible in the winter months from lake ice. You can't see in this image, but PW10, you have to cross the lake between the alignment and the pit, and GSC 4, you're crossing another lake, Jimmy Lake, so to get to the pit from the road alignment. Variability of material sources. So in this case as well, it's another challenge. We know what materials ideally we want to work with, but then there's the materials that you have available to you to work with. And every pit was a little bit different in its gradation. And then within the pit, there was a bunch of variability. So this is just an example of one of the better material sources along the alignment, pit 312, and you can see here that there are portions really well graded material with low fines, getting up into the nice sized gravel size. Excellent material, but not all the material within the pit was that way. And sometimes drill holes and certain zones encountered a very fine, poorly graded soil. And so then we had to, for the pits, but for the project as a whole, understand and rationalize what materials we were going to use and how we were going to be undertaking some quality control in terms of what was acceptable and what was not, in order to give the contractor the direction of what they would be permitted and not permitted to do. So and you can see this, there's a spec band here on the red lines, but we're looking for a material with less than 35% fines, max moisture content, about 35%, and low visible ice. So we use 10% as a number. I'll get to ice and the issues with ice and soil. But those are kind of the parameters that we ended up rationalizing and distilling to, that then were something that was measurable and executable from a QC perspective in the field. There was some good work that was done in the early 1980s on the compaction using frozen soils, or the compaction of frozen soils, and it was by Botts and Haas, and they did the work through the Cold Regions Research Engineering Laboratory in the US. And it's a good special report, and we used this and then worked with it as well, because we needed to understand what sort of densities could we effectively, realistically achieve under winter construction, and what were the big factors influencing the density that you can achieve in winter conditions. So we recognize that earthwork in this job, but on most projects, earthwork is a critical part of construction, and particularly for this, for the winter construction, it was. We understood excavation, and that we could excavate in the winter months. We can excavate rock in the summer or winter. We know that we can drill and blast and excavate frozen soils in the winter, but it's the placement of the soil, that winter construction, in a winter environment that's very restrictive and difficult, and that's what we wanted to better understand. We did know that it's not possible to compact to the same density in a winter as you would in the summer, and that's why conventionally down south we don't place soils in winter freezing conditions, or we hoard or do some other activity in order to be able to place soil in an unfrozen state. Part of this compaction and density that you achieve in the winter with frozen soils, we also needed to understand, well, then how much settlement are we going to, is the material going to stay stable when it thaws? And then how much settlement are we going to experience in that material? Let me just move here. And so, and it's not always, and so the project needed to address this, that we needed to compact the material, and we needed to understand what compaction or densities we could achieve, and how it was best to do that, and how we can maximize compaction or density of the soil. I'll shift to the next slide. Because we knew the material was going to settle, then part of the design was to construct an overbuild on the road embankment. And so you're looking at a typical cross section here. We overbuilt the embankment by 45 centimeters, in this case, to account for that thaw and that settlement that was going to happen in subsequent years. And we ended up with, after all the thermal and stability analysis that was done, we ended up with a pretty conventional embankment. 3-to-1 side slopes is what we felt comfortable with. The crest width was 8.5 meters. That's just wide enough to support 2-lane traffic on a gravel highway. And in this case, it doesn't show up, but in this case, we also placed a non-woven geotextile separator between the embankment fill material and the tundra. Like I said before, all the construction happened in the winter months. Just some photos to show or illustrate the work that happened in the winter months and how we tried to maximize densities in the field with frozen materials. The work that was done by Carell and the work that we did, we recognized that if we took blasted material and we were able to place it in thin lifts and shear it into place, and then further crush the particles to crush the frozen particles, even though they're ice bonded and then there is some ice crystals and stuff within the soil. If we're able to shear it in place and compact it, with a, like in this case, we used a sheep's foot vibratory compactor. 10 ton is what we use here, and we did this in lifts building up. That this was the way that we were able to achieve the best densities in place of the embankment. That was of course attractive to us. The higher the density, the less the thaw settlement that we were going to get in the subsequent years. So this is just an example of the material being spread, and the sheep's foot roller going back and forth. And of course, this is the pattern. Everything was passed with at least a minimum of 4 passes. Lifts were started off at a maximum 40 centimeter thick lifts, and then they were packed down. In 2017-18, and so we were working with the GNWT to understand, how much compaction and settlement we were going to get, how much material we're going to use. The GNWT was interested in understanding volumes and costs. The GNWT also was interested in doing some density testing of frozen soils. And so this work was done actually through the University of Calgary in 2017-2018 by 2 students. GNWT provided funding to the U of C to study the behavior of compacted frozen soils obtained from the ITH. So the GNWT provided samples from 6 borrow sources. And then 2 students, Dylan Kennedy and Joshua Winfield, spent the summer undertaking lab-controlled testing of those soils in an unfrozen, but then in a frozen environment, where they used a freezer, and then they did standard and modified compaction tests or Proctor tests in the lab to better understand how this material would behave with increasing ice content. So the image on that you're seeing here, those are standard Proctor curves of a material that you would of an unfrozen material that you would expect down south. In moisture contents, optimums in that 10 to 8% range, and then you're going to get dry unit weights in that 2100 to 19 to 2000 range. Okay, but we needed to understand how much loss and density occurs when you start introducing more moisture in the form of ice in the material. And and this work builds on actually the work that Carrel did in the 1980s. So we weren't doing anything novel here. We were just reproducing the work that they had produced in the 80s. But you can see here clearly that if with about less than 2% moisture, moisture content in the soil, less than 2% dry, then you can achieve pretty good densities, even though the material is below 0 degrees Celsius. You can't get to the optimum because you don't have the optimum moisture contents to achieve that, but you can get pretty good densities. But you see that every increase in moisture content, which is an ice form in frozen state, you got a pretty significant decline in the achievable densities. And so this was, and so we realized that even that. And then we did further testing that I'm not showing here, but in the field, that even at optimum moisture content, if you're at optimum moisture content, we were only able to get about 70 to 80% of the maximum dry density of that frozen material, which then fit into and supported the 45 centimeter overbuild that we estimated would be needed for the highway. At the end of the day, after 140 kilometers of highway were constructed, in places the overbuild was sufficient, and in other places it was insufficient, that there was more settlement that occurred, probably because either the moisture contents were higher or the in-place densities, frozen densities, were lower, a variety of factors. I'd like to speak a little bit on the bridges of the ITH. On the ITH, I didn't mention it earlier, but there are 8 bridges along the Inuvik Tuktoyaktuk Highway. 2 of them are single span and 6 of them are multi-span bridges. You can see an example here of a multi-span bridge with the piers and any abutments. All here is all the bridges are precast concrete girders. They were all manufactured down south, brought to site. All this construction happened in the winter months, as you can see in this image, the snow conditions. There was different options that were looked at. Is it possible I guess mix concrete from a batch plant locally? Was that cost prohibitive? Is it more effective, which is what was done here, just to precast concrete and ship it to site? So those different cost scenarios were evaluated. The bridges, they're all precast concrete bridges, but they're all on piles. But the piles, and this is the unique portion that I wanted to speak to about, or unique that maybe not everyone on the call would recognize. The piles are these ones in the photo, they're all 356 millimeter diameter piles. They go 12 to 18 meters below grade, let's say, and they're all what we consider steel pipe adfreeze piles. And I'll get to what we mean by adfreeze piles shortly. And then you can see here, and I'll speak to these later, these were access tubes installed in behind the piles. So they were spaced about 1.9 meters apart and about 1.2 behind the piles. And these were access tubes that were placed now because we wouldn't be able to get access under the bridge deck to drill these holes after the fact. That then would provide us the opportunity to do some thermal ground cooling intervention if we needed to in the future. So what's an adfreeze steel pipe pile? They're commonly used in the Arctic. They're well suited for relatively light loads. They're common in communities. And an adfreeze pile is constructed in permafrost by basically drilling an oversized hole, inserting a steel, in this case, steel pipe pile, and backfilling the annulus and the inside of the pile with a saturated granular backfill, which freezes following installation. It takes time to freeze back, and I'll explain that. And then the pile derives its capacity from the bond between the pile and the frozen backfill and the adjacent soil. So primary design inputs are ground temperature, pore water salinity, or the chemistry of the soil is important, and then of course the loading conditions, the short long-term loading condition. And then the diameter of the pile influences its capacity. So capacity is dependent on the configuration of the pile, its diameter, but the nature of the load being applied and the characteristics of the permafrost. Is there salinity to it? Is there some other chemistry? You know, what are the permafrost conditions? These piles and anything under a load on ice creep, and so these piles creep as well. But the design accepts, in this case, an allowable creep settlement for the life of the structure of these bridges, and we assumed a creep rate of 1 millimeter per year. And adfreeze steel pipe piles are designed to perform in a range of secondary creep. So then that rate of settlement stays constant over time, which is important. You don't want to get into that tertiary realm, and so so that's what was designed here. We also know that ice and permafrost has got higher resistance to short-term loads rather than long-term sustained loads. But these bridges, the bridges weren't that heavy. The traffic live loads were proportionally high to the overall traffic. So the short-term duration of the load events was considered to justify the high capacities for for the piles for traffic loading. So the piles, because the vehicle is a dynamic load that travels over the bridge, even though that vehicle can be heavy, it's happening in a dynamic short-term fashion, and then so those piles then are able to resist that load. How are these piles installed? A conventional piling rig, like you see on the image to the left. If the pile is 14 inches in diameter or 356 mils, then it ends up being a 18 or 20-inch hole, and 400 or 500 millimeter diameter hole. And then once the hole is bored, here's an example of that's an 18-meter long steel pipe pile that is going to get lowered down the hole. Once the pile is lowered, then it needs to be the backfill. The slurry needs to be placed, and so you can see they're leveling here with the wood shims, and then in this case, the backfill was a 20 millimeter crush, limestone crush obtained from Inuvik, and then that was placed between the annulus of the borehole and the steel pipe, and then water was pumped down the hole. And then the same was done on the inside of the pipe, even though the pipe had cutouts to ensure that it was completely backfilled. Then you can see here a funnel was created. The material is dumped down the funnel, down the hole, and then everything gets flooded with water. And of course, the water is the photo here. It shows a water truck. The water is warm. We try to keep it as cold as we can, but inevitably it ends up being 5, 7, 8 degrees. So it is warmer than the permafrost. We put it down the hole. It warms the ground. The warm water warms the ground in the short term, and then we have to wait for freeze back to occur. And freeze back of a steel pipe pile, it can take about a week. It depends how much water and how hot the water was down the hole and what the ground temperatures, the native ground temperatures are. So here's an example of just monitoring freeze back. So at time 0, everything is at the 0 isotherm, and then after 5 days, it's cooling like this, but the mid portion here is still close to 0, just barely frozen, and then a day later, it's getting colder. And so once we achieve about -1 as a temperature profile, then the pile is good to start loading. We don't load the piles until we have to. So the longer we can wait, and the colder that the piles can get and equilibrate back to the natural ground temperatures, the better. Temperature instrumentation sites along the way. There's a bunch of sites. I'll just go through these fairly quick. The government is keenly interested in monitoring ground temperatures across the entire alignment at the bridge crossings. All the piers and all the abutments are instrumented for ground temperature. Several locations along the highway as well. And then the Northwest Territories Geological Survey have a bunch of instrumentation along in riparian zones along the highway. I'll show you 2 images of ground temperature over time. This is one within the embankment that you can see that over the period of four years, and this is a 2.4 meter thick embankment, we're seeing warming penetrating below what is identified here as the original ground. But we don't know in this case, so we're showing warming here. This section of the embankment is performing well, but we don't know here, or haven't investigated this yet, whether this settlement or this warming, is it just due to settlement of the embankment? Is the embankment not 2.4 meters thick now as it was constructed in 2017, which is likely the case? The embankment is going to settle about 20%. And so really, we're probably, even though it's showing thaw penetration into the OG, this 0 degree temperature is probably pretty close to the original ground. At bridge crossings, and I'll wrap up here, at bridge crossings, all the abutments and all the piers are monitored. Ground temperatures are are cold. We want the colder the ground temperature, the higher the capacity of the adfreeze steel pipe piles. And this is an example of just one crossing, anomalous to the entire project, where we're seeing warm temperatures in the upper portion of the pile, which is suggestive to us. And this area is being investigated. It's called Hans Creek, is Bridge Crossing 38, that there might be a talc here that was not picked up during the geotechnical investigation, but these sites weren't drilled at the exact locations of these piers. But this bit of a warming of a talc, then of course it compromises the strength of the pile or the capacity of the pile. I'll get back to the thermal tubes really quick, and like I mentioned, they're intended to be used if ground cooling intervention is required down the road. They weren't installed day one because it would come at a cost, but these caps could be removed and thermal probes placed down these tubes, and then thermal siphons could be connected to them. So what's a thermal siphon for those that may not be aware? Just in short, it's a thermal siphon is a passive cooling device that operates on a principle of convection through vaporization and condensation. And so a sealed thermal siphon contains pressurized carbon dioxide, and it's partially in a gas and liquid phase. When the air temperature is colder than the ground, heat is extracted from the ground through vaporization of the carbon dioxide in the evaporator section, which is here. Okay, and then it rises up into the radiator section, into the upper portion of the thermal siphon, the radiator section, which then exposed to the cold ambient air atmosphere, and then which causes the gas to condense, and then condense to a liquid, and as a liquid, then it returns back to the bottom of the thermal siphon, setting up this circulation. This heat transfer occurs in the low end of the unit, like it's warmer. The heat transfer and this exchange occurs when the ground is warmer than the colder air on the outside. So these guys, passive systems, only operate in the summer months, not in the, in the winter months, not in the summer months. So the ground has to be warmer in order for this phase change to occur, and then the ambient air temperature has to be colder than the ground. So passive thermal siphons work in the winter months. Thermal siphons is a proprietary technology, and the company is Arctic Foundations. Arctic Foundations of Canada is who we use. Arctic Foundations has an American company as well in Alaska. Really briefly, I'll speak about just road maintenance. Any new road requires maintenance, and I'll show you some photos. So this is the gravel surface. You can see that in years 1 and 2, there's going to be some instability, some softening of the embankment, a little bit of a rutting and water and erosion along the edge of the embankment. And these things were all they're identified, and then they become, and then they're handled just through the maintenance and operation of the road. Ponding water is also an issue, and of course, ponding water is a heat sink, and that does degrade permafrost over time. So we try to mitigate that and move the water as best as we can. And then, of course, snow management in the winter months is an issue as well. So in places of the highway, the snow accumulation doesn't really exist, and the wind nicely blows the snow away. But in other parts of the highway, we're seeing that there's a fair bit of snow accumulation. And then, so from a highway maintenance perspective, that needs to be managed. And in places, the snow accumulation can be quite high. You can see the top of a road sign here. So this is 6-7 feet of snow. Takeaways really quick. Winter embankment construction is feasible. Terrain and material variability is not entirely accounted for in the design, nor really could it be. Even though we did all the terrain mapping and we did all the geotechnical investigations, you can't pick up every permutation. Borrow sites can be effectively developed in the winter We've known that, and others develop in the winter. Winter compaction has its limitations, so you have to account for it in design. And then design needs to be, you need to design for resiliency, but you also need to design to be adaptable or for adaptability. Newly constructed roads, like any new piece of infrastructure, it is going to require maintenance. And unforeseen conditions will arise inevitably, and we just need to be prepared to adapt to those conditions when they arise. That's it. Hopefully it's not too long. Yeah, 51 minutes, a little long. Thanks, Daniel. And I'll take any questions.
Okay, over here, the Tony Singh is asking that, have you seen any significant differential settlement during thaw so far? And does the overbuild account for that?
Yeah, so right, so we've seen a lot of difference in settlement along the 140 kilometers. And like I mentioned briefly, the 45 centimeters of overbuild worked well in some sections, and other sections we experienced up to 75 centimeters of settlement, which obviously then required more fill to be imported in. So there was a lot, even though we accounted for an overbuild and for thaw settlement, because of the variability in soil type and in ice content or moisture content in the form of ice, and even in compaction differences, that just translates to a lot of difference in settlement from in the order of maybe 30 centimeters to as high as 70 centimeters along the 140 kilometers.
Okay, actually we are actually running out of time. Maybe one more question, because we only have like 2 or 3 minutes left. So if you have any question, we can only take one more question. Okay, we have one question from the. We have one question here.
Okay. Thanks, Ed. Very nice presentation. Are these reports available to the general public? This is what I'm curious about. The Geotech report and the pilot design and these all these.
No, not like the Corel report is available, the compaction of frozen soils, but the reports for the highway, like the adfreeze pipe pile design reports and the design reports for the geometric design of the road and stuff, those are GNWT materials, and so they might share them, but they're not publicly available.
The temperature, and I assume the temperature data is also becomes a problem with GNWT.
Yep. The temperature data is more available. The government is willing to share temperature data between Inuvik and Tech. Even we or I, but we have to ask for it as well. Right now, the Aurora Research Institute in Inuvik, they are the ones that are collecting ground temperature data along the ITH for the GNWT. So and they are pretty good at sharing ground temperature information.
Okay, thank you. Then the one last question regarding the steel pipe, right? We did some research work on the piles and the permafrost, right? For this long, like a 12-meter long, I say that this pile is typically like a 12 to 18 meters long and 356 meters diameter. Do you have any sense about what is the average, typical average, shear force, shear stresses on the sites? Allowable, at least at allowable was, are we talking about like 20 kPa or 20 kPa this magnitude? Do you have any?
I only caught part of that. Are you talking about shear stresses on these adfreeze steel pipe piles?
Yeah.
Yeah, right. So the shear, yeah. So let's say 25 kPa for see, it can vary a lot, and it's not really driven. Adfreeze steel pipe pile design is not driven just by the total load it can carry. It's driven by creep and creep parameter and creep over time, and which is connected to the design life of the structure. So you're wanting something to be there for a long time. How much deformation can it withstand? Or how much deformation can it withstand in the form of creep? And how much can be the total creep displacement over time, right? And so, that's kind of a short answer. It depends. It depends on what you're needing to support.
Okay. Thank you everyone for your wonderful presence. And we have to stop here. If you have any more questions, you can directly email Ed and get your answers. And for now, we have to stop, and please join us next week for the next event. Thank you.
Right. Thanks, everyone.